All right, well, we're done waiting. Let's go ahead and get started with today's material. Now, chapter 5 that we started is all about functions, right? And all your homework, functions and function composition. Let's remind ourselves of what exactly a function is and some of the properties that we care about on functions. So first off, what's a function?
It's a relation from A to B where A is only matched with one thing from B. Perfect.
So that would be a function from A to B, but you got the right idea for a function. It's a relation where every input maps to a unique output. The intuition I like to give you is, when is a relation a function? If the inputs being the same means the output's the same, then it's a function. You can't have two inputs the same and the outputs being different, otherwise it would not be a function. I can't have one maps to 2 and one maps to 7. Make sense? So, quick question. Here's a relation right here, set of ordered pairs. Is f there a function?
Is what?
F is equal to this set of ordered pairs. Here's our relation f. Is this relation f a function?
No.
No, why not?
2, 3, 2, 4.
We have 2 goes to 3 and 2 goes to 4. So notice I have two inputs being the same, mapping to two outputs that are not the same. So it does not satisfy this condition. It is not always the case that if two left-hand elements are equal, then the two right-hand elements are also equal. If that were the case, then it would be a function, so this is not a function. Right? If I remove this element, and it were that, now it's a function. Make sense so far? Just review from last time. Now, one of the properties we cared about a function having was it being one-to-one. What did it mean for a function to be one-to-one? It means if the outputs are the same, then the inputs must be the same. Is this function up here a one-to-one function?
Yes.
Yes, I never have an output coming from two different inputs. If I switch this 3 over here, made 3 also map to 3, now this is not a one-to-one function. It's still a function. Every left-hand element only goes to one right-hand element, but I have the same right-hand element being mapped to from two different left-hand elements. The most common example that you come across of a function that is not one-to-one is f of x equal to x squared. Because what is f of 3 equal to? 9. So f of 3 is equal to 9. What is f of negative 3 equal to? 9. So f of 3 is equal to negative 3, but it is not the case that 3 is equal to negative 3. This implication is not true. If the implication is always true, then it's one-to-one. If you can ever find a case where it's not true, then the function is not one-to-one. This coming back to you? Okay. And then we have this notation, a function from some set A to B. When we see a function from A to B, what do we instantly know? It maps everything in A to something in B. It does not have to use all of B, it has to use all of A. So if I see a function from A to B, I instantly know the domain of f is all of A, and the image of f is just a subset of B. Maybe all of B, maybe it uses all of B, maybe not. Coming back? A little? Let's draw a picture for this really quick. Come look down here. So here's some set A, 1, 2, 3, 4. Here's some set B, 4, 5, 6, 7. Here's f mapping from A to B. It maps everything in A to something in B. Now in this case, f happened to use everything in B. But I could have drawn f maps 1 to 4, 2 to 4, 3 to 4, 4 to 4. That would have been a function from A to B. So you don't have to use all of B, you have to map everything in A to something in B in order for it to be a function from A to B. Your domain, or all your left-hand elements, will always be all of A. Your image, or all your right-hand elements, will always be some subset of B. Maybe all of B, but at least a subset of B. That make sense? Okay, that was this notation. And then finally, our last property that we cared about functions having was the function being on 2. When is a function on 2? So a function from A to B is on 2 when the image of f is all of B. So in this case, f happens to be an onto function because it uses all the b. So onto, it just means it uses all of your second set here. That second set is called a codomain if you care. So it uses your entire codomain is what it means for it to be onto. It uses all the b. That makes sense? And then finally, bijection. It's not really a new property. It just means a function is both one-to-one and onto. Now, I told you I'm never going to write out 1 to 1 like this anymore. I'm just going to do 1-1 to mean one-to-one. That's what everyone writes it. So bijection means it's one-to-one and onto. If it has both those properties, it's called a bijection. That means it maps everything. If f from A to B is a bijection, that means it maps everything from A to everything in B in a one-to-one way. You'd be both one-to-one and onto. Bijection, good? Now the one that confuses kids the most. Function composition, that little circle symbol. It takes two functions and it combines them together into one new function. Here's its exact definition. G composed with f of A is equal to G of f of A. Now I told you, the way to think about this is it's like doing two functions in one go. So here I pictorially drew up some function f from A to B and some function g from B to C. We're going to recalculate g composed with f. So this here is a function, and we're just going to write out exactly what that function is. And what does this function do? Remember, you have to think about composition right to left. It does f, and then it does g. Some people read this as g after f, instead of g compose f. So this function says start with f, then when you're done with f, do g. So let's run it through. So we're doing g composed with f, or we're doing g after f. What does this do with 1? Well, first it runs it through f. Where does f map 1 to?
5.
5. It maps 1 to 5. And then it does g. So we mapped 1 to 5, and now where does 5 go? 4. And so g composed with f of 1 is 4. Rather than mapping 1 to 5 to 4, it maps from 1 directly to 4, doing both functions in one go. That's all it is. So what is f composed with g, or g composed with f of 2? 6. 3. 8. 4. 2. See it? That's all function composition is. Combining two functions together into one function, cutting out this middleman. Good? Okay. I had one more example here, so let's let A be the set 1, 2, 3, 4, 5. And let's say that f is a function from A to A, and it's a bijection. So, what do I know about f? If it's a function from A to A,
You know that it's 1 to 1 and 1 to 2.
well, I also say it's a bijection, so it's going to be 1 to 1 and onto. But first, just what does this piece of information give us? If I tell you f is a function from A to A, what do I instantly know about f? It maps everything in A to something in A. So if A is a set 1, 2, 3, 4, 5, I tell you f is a function from A to A. Here's its domain. In other words, so far I know f has to map 1 to something, it has to map 2 to something, it has to map 3 to something, has to map 4 to something, has to map 5 to something.
So F, so A to A just means that everything in A has to be mapped to something.
In A, perfect. So here's our set A, 1, 2, 3, 4, 5. If f is a function from A to A, it has to map everything in A to something in A. Now I also gave you more information. I told you f is also a bijection. What does that mean?
It's 1 to 1 and on
It has to be 1 to 1 and on 2. So could f be the function 1 goes to 1, 2 goes to 1, 3 goes to 1, 4 goes to 1, 5 goes to 1?
No.
Why not?
That's not 1 to 1.
It's not 1 to 1 and it's not on 2. On 2 means it has to use up all of A on the right hand side. And 1 to 1 means all the right hand sides have to be unique. I use the same right hand side over and over again. So whatever my right hand side is, let's think this through. Starting with what could 1 possibly map to?
2, 3, 4.
It could map to, I could map it to 1, I can map it to 2, I can map it to 3, I can map it to 4, I can map it to 5. But I have to map it to one of those things, right?
Yes.
Okay, So how many options do I have for what I map 1 to? 5 options. So whatever I put there, I have 5 options for what goes there. Now, once I pick something, like 2 or whatever I pick, so say I pick 2 there, now how many options do I have for what goes here? 4 options, because I can't reuse the same thing if my function is going to be a bijection. So I now have 4 options for what goes here. And then how many options for what goes here? 3. And then?
2.
And then? 1. For a total of how many options did I have? How many bijections could I make? 5 times 4 times 3 times 2 times 1.
Yeah.
Right? What is 5 times 4 times 3 times 2 times 1? It's 5 really loud. 5 factorial, right? 5 factorial means 5 times 4 times 3 times 2 times 1. Remember that notation? So that is how many of these bijections I could make on this set A. Notice how many elements were in A? 5. And so, how many bijections could I make on A? 5 factorial. What if A had 6 things in here? Then for my first element, I would have had 6 options. My second one, 5, 4, 3, 2, and there would have been a 6th one here that had 1. And so then I could have made how many bijections?
6 factorial.
6 factorial. And in general, if A had n options in it, then I could create n factorial bijections on the set A. That make sense? Okay, so that brings us to today's topic, permutations. That's what our next section is about. We're just covering one section today. So all that was just review. Okay, permutations. This is going to feel like a very strange chapter to cover in terms of the notation. Permutations is one of those things that 2 months from now, you're not going to remember the things we covered in today's lecture. And that's fine. It's going to be one of those things that we cover it now, and it's not really going to matter going forward for the rest of this course. So why do I cover permutations? The reason we cover permutations is I am simply trying to get you very comfortable with working with functions and function composition. And so permutations is going to give you a ton of exposure to that. So that's the point today. So today's going to be one of those lectures where keeping up with the notation of the lecture is kind of hard. It's going to be difficult for you, but the homework's going to be much easier than what you see on the board. It's going to be one of those kinds of lectures. So if you struggle to pay attention to the lecture, you'll be fine on the homework. If you sleep through the lecture, you're going to be beyond confused on the homework. So, fair warning. Plus test next week, don't forget that. That's not me scaring you, that's a fact. So don't forget that. It's not a threat, it's a syllabus, it's a statement about the syllabus. So don't forget that. Okay, so what is a permutation? Let A be a set and F be a function from A to A. Then F is a permutation on A if and only if F is a bijection. It's exactly what we were talking about down here. Permutation, it's a bijection on the set A. That's a permutation on A. That's it. Nothing new. Just a different terminology for something you've already covered from the previous section. So pick some set A. What is a permutation on A? It's just some function from A to A that's a bijection. It's just one of these. That's it. Good so far? Okay. So going back to our example, let A be the set 1, 2, 3, 4, 5, just like we had down there. And now I'm going to pick some random permutation. So here's a random permutation. Notice it maps everything in A to everything in A in a one-to-one way. 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. Good? It was just one of the 5 factorial permutations we could have found on the set A. I just picked a random one, wrote it there. Good so far? Now I said it's pi. As a matter of convention, when we are using variables to represent permutations, we use lower Greek letters. Lowercase Greek letters. Or actually, I'm not sure if that's a lowercase tau. But we use these Greek letters, typically pi, sigma, tau, and iota, to represent permutations. It's just to help you from context instantly know what we're talking about. When you see me talk about something like x plus y, you instantly know, oh, he's talking about real numbers. When you see me doing something like m plus k, you know, oh, those are probably integers. When you see me write pi as a function, you know, oh, he's talking about a permutation. He's talking about a function that's both one-to-one and onto. Just helps you know from context. Keep track of what it is we're talking about. So here's pi, just a function, permutation. Maps 1 to 2, 2 to 4, 3 to 1, 4 to 3, 5 to 5. That's what the function pi does. And I know you're used to thinking about pi as a number, so let's just go through this exercise writing out what each of these is. So what is pi of 1?
2.
2. It's what pi maps 1 to. What does pi map 1 to? It maps it to 2. So pi of 1 is whatever pi maps 1 to, which is 2. Good so far? All right, what is pi of 2? 4. Perfect. What is pi of 3?
1.
Pi maps 3 to 1. What is pi of 4?
3.
Pi maps 4 to 3. And what is pi of 5?
5.
5. And so if I were to write out the list, what does pi map 1 to, pi map 2 to, 3 to, 4 to, 5 to? It would be this list. 2, 4, 1, 3, 5. It mapped 1 to 2, 2 to 4, 3 to 1, 4 to 3, 5 to 5. Okay, why do we call these things permutations? We've used the word permutation before. What did we use permutation for? What's a permutation in colloquial language? Just day-to-day talk. What does someone mean by a permutation? They mean just an ordering of something. So what is a permutation of the numbers 1, 2, 3, 4, 5? It's just a way of ordering them. Here's one permutation of the numbers 1, 2, 3, 4, 5. I can have 5 goes first, then I can have 3, then I can have 1, 2, and then 4. This is one possible ordering, one possible permutation on the numbers 1, 2, 3, 4, 5. You with me? And that is why we call these functions permutations, because that's all they do, is they give you a reordering of the elements of the set. So I think about 2, 4, 1, 3, 5 as being a reordering of the numbers 1, 2, 3, 4, 5. Think about it as an actual list, an ordered list. So that's why we call them permutations. It's one way to order the elements in the set. And if I have the set, going back to our old counting problems, if I have a set here that has 3 objects in it, 1, 2, 3, whatever they are, how many different ways can I order those objects?
3 factorial.
I got to pick something to come first, so I have 3 options for what comes first. Once I pick that, so 3 options for what comes first, how many options for what comes second?
2.
2. How many options for what comes third? 1. And so it's 3 times 2 times 1, or 3 factorial. That's how many different ways I could arrange those objects, or that's how many different permutations I could create on that set. If I had a set of 5 things, there would be 5 factorial permutations. If I have a set of 3 things, there's 3 factorial permutations. This is now the mathematical object that we use for keeping track of ordering. Make sense? So that's why it's called a permutation. And you've already kind of been using permutations in your thinking. Same type of thinking, just ordering of things. Good so far? And so that's going to be a good way to think about a permutation, is it's just a reordering of the elements in the set. Pi is the permutation that does this ordering, 2, 4, 1, 3, 5. It maps 1 to 2, or in other words, it puts 2 in the first position. It maps 2 to 4, or in other words, it puts 4 in the second position. It maps 3 to 1, or in other words, it puts 1 in the third position. Make sense?
Mm-hmm.
Okay. So, pi just reorders the numbers 1, 2, 3, 4, 5. Think I've stressed that enough. All right. Definition now. Let A be some set that has the numbers 1, 2, 3, dot, 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 all the way up to n. So there's n things in there. Good so far? We will use S sub n as a shorthand for talking about the set of all permutations on A.
Okay.
So if this is A, S sub n is a set of permutations on A. It's a set of all possible permutations you can make. So if A were the set 1, 2, 3, 4, 5, going up to 5, then pi here would be one of the things in S sub 5. Alright, so another concrete example. Say that A were the set 1, 2, 3, 4, and it stopped at 4. What is S sub 4 then? S sub 4 is all the permutations you can make on the set 1, 2, 3, 4. Stop at whatever number's right there. So this function, this permutation, would be one of the things in S sub 4. The one that maps 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Here's one possible permutation you can make on the set 1, 2, 3, 4. So that would be one of the things in S sub 4. S sub 4 is going to be the set of all possible permutations you can make on the set 1, 2, 3, 4. Question: how big is S sub 4? How many elements are in it?
4 factorial.
4 factorial. Because there are 4 factorial permutations you could make on the set 1, 2, 3, 4. S sub 4 is a set of all those permutations, with this being one particular permutation. The one that maps 1 to 2, 2 to 3, 3 to 4, 4 to 1. Or you can think about it as puts 2 first, 3 second, 4 third, and 1 fourth. One possible permutation, one possible ordering. Whatever it maps 1, 2 is the first element. Whatever it maps 2, 2 is the second element. Whatever it maps 3, 2 is our third element. Whatever it maps 4, 2 is our fourth element. Good? Just like what we did up here. Whatever pi mapped 1, 2 was our first element. Whatever pi mapped 2, 2 was our second element, etc. Okay. The identity function on A, remember what's the identity function on A? It's the function that maps everything in A to itself. So if A were the set, where do I have an example? If A were the set 1, 2, 3, 4, 5, what's the identity function on A? It's a function that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5.
Okay.
And the identity function, notice, is always going to be 1 to 1 and on 2. It's always going to map everything in A to something in A to in a one-to-one way. So the identity function is always and forever going to be a bijection, so it's always and forever going to be a permutation on the set. Okay.
And the permutation. Oh, yeah.
It's going to be one of those permutations. So the identity function on A is a permutation, and we typically denote it by iota. So I told you these are going to be the Greek letters I use over and over again to symbolize functions. We typically save iota to represent the identity function on whatever set we're talking about.
Okay.
So when you see iota, almost always means the identity function on whatever the set is that we're talking about.
Isn't that? It looks like a C.
Sorry. It's supposed to look kind of like an I with no dot.
Sounds
So
like an L.
here's an I, get rid of the dot, that's an iota.
Oh, okay.
And you'll have to just get used to my poor handwriting and guess from context what the symbols are I'm scribbling down. I think it'll be pretty clear from context that it's an iota. Iota. Okay. So, for example, if I grab iota out of S sub n, remember what's S sub n? It's a set of all the permutations you can make on the set 1, 2, 3, 4, 5 up to n. So if iota is in S sub n, what is iota?
1, 1, 2, 2.
Is a function that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, dot, 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 all the way up to n, for whatever n was. If this was iota in S sub 20, then iota would be the thing that maps 1 to 1, 2 to 2, 3 to 3, dot, 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 all the way up to 20 to 20. Concrete example. Somewhere along a proof, you see me write this. Take iota in S sub 4. You instantly know what function is iota. It's one that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4. So for every S sub n you choose, something like S sub 7, it's going to have its own iota. Make sense? Okay. So now let's look at some properties of S sub n. First and foremost, the one I've been stressing over and over again, how many elements are in S sub n?
And factorial.
N factorial. That's the same thing as saying, how many permutations can you make on an n element set? N factorial. Because this is the set of all permutations you can make on an n element set. Overstress as much as I can. Okay, let's notice another property of S sub n. Remember what that symbol means? For all. For all pi and sigma in S sub n, or in other words, for any two permutations you pick out of S sub n, their function composition is also going to be in S sub n.
Oh, yeah.
If you pick two permutations in S sub n and compose them together, the result will be another function, another permutation in S sub n. Does that make sense?
Yeah.
Sounds like a weird way to say it's closed.
That's exactly what this is saying. For those of you who have done some more advanced math with me, this is saying that function composition is closed on S sub n. That's exactly what it's saying. You take two functions in S sub n, compose them together, you get another function in S sub n. Now, how could we quickly validate that? How would we validate that their composition is in S sub n? We need to show that their composition is 1 to 1 and on 2.
Oh, it's a bijection.
Yeah, a bijection composed with a bijection on the same set is always just a bijection on that set. You did, as one of your homework problems, proving that if you compose together two 1-to-1 functions, then the result is 1 to 1. Right? And then pi maps everything in the set S sub n to everything in the set S sub n. Or sorry, everything in the set. What would be our set in this case? It would be the set 1, 2, 3, ... n. So pi maps everything in there to everything in there. Sigma maps everything in there to everything in there. And so the image of your whole thing is going to be all of n. You can write that out as a quick proof so that you can get anything out of there. But so that's how we validate. The harder one is probably validating the 1-to-1. Did I not give you that problem as one of your homework problems? Let's scribble that to the side really quick. Proof. We're going to prove F 1-to-1 and G 1-to-1 implies G composed with F is 1-to-1. And we'll do like a scratch proof since we don't have ton of room. Should have done down here, more room. Okay. How do I know that how would I prove G composed with F is 1-to-1? I need to show if two outputs are equal, then their inputs are equal. With me? So I say 1, let A and B be two things in the domain of F, because we start with F. When we do F composed with G, we start in F's domain, right? Such that G composed with F of A is equal to G composed with F of B. So pick two things out of the domain that have the same output when you run through the function. How do I show that G composed with F is 1-to-1? I need to now show A is equal to B. So pick two things that happen to map to the same thing when you're running through the whole function, and I need to show that those two things are the same thing. Well, I know that. What's our definition of this? I know that's the same thing as G of F of A is equal to G of F of B. Right? That's what it means for G composed with F of A to equal G composed with F of B. Now, since G is 1-to-1, that's one of my given things, G is 1-to-1. Since G is 1-to-1, if these two outputs that you run into G are equal, then what do I know? My two inputs for G have to be equal. So then that gives me, since G is 1-to-1, that gives me that F of A is equal to F of B. And then once again, since F is 1-to-1, if I know F of A equals F of B, what do I know? That A equals B. And so there we go. If that's equal to that, then that's equal to that. So the function composition as a whole is 1-to-1. I don't know why I didn't give that to you as a homework problem. Because I have it in my notes, I did.
Might have been the extra credit, but
Maybe it was the extra credit. Shoot. You remember that for next time. Anyways, so you're supposed to have done that. So function composition of two bijections, still going to be a bijection on the same set. So it's going to be closed on that composition. Good so far? Compose two permutations together and the result is a permutation. In other words, let me say it in language you can plainly understand. Reorder the elements on this set and then reorder that reordering. And you still just have a reordering of the elements on the set. That's probably the easiest way to say it. Okay, what does our next one here say? Property 3. Pick any 3 permutations you want. Pi, sigma, and tau. Then tau composed with, sigma composed with pi, is equal to tau composed with sigma composed with pi. Or in other words, it's associative. And we proved that one for sure last week when we proved composition in general is associative. And so it's going to be associative on the special case where you have permutations. Because it works for functions in general. So it doesn't matter in the special case that's permutations. Function composition is associative. Good? Our next one here, again, one that we proved last time. For any pi in S of n, the identity composed with pi is the same thing as pi, is the same thing as pi composed with the identity. In other words, composing with identity doesn't change anything. Come back over here at this picture, and say we had F mapped like this, G mapped like this, but then I took G and I mapped it on the identity on C. What does the identity on C do? It maps 2 to 2, 4 to 4, 6 to 6, and 8 to 8. So rather than doing F, G, then identity, or sorry, rather than just doing F then G, let's do F, G, then this identity. Now what does 1 map to? Well, 1 maps to 5, maps to 4, maps to 4. It didn't change anything. It still maps the same way that the functions mapped before. That's what this is saying. You compose with identity, it doesn't change anything. You're just adding one more step. You're still going to end up with the same result. If I took the 4 and mapped it to 4 at the end, that didn't do anything. Similarly, what if at the start I first mapped 1 to 1, and then I went to 5, then to 4?
We'll change it.
Doesn't change anything. So it doesn't matter if you do your identity function first or if you do it last, it doesn't change your function. And so it doesn't change your permutation. Good? And then finally, for every permutation, that inverse permutation is also a permutation. What's the inverse permutation? That's one where you just swap all the elements. Rather than having a, where do I have one written? Here's one. Rather than having a 1 goes to 2, I swap it and have 2 goes to 1. Rather than having 2 goes to 4, I have 4 goes to 2. Rather than 3 goes to 1, I have 1 goes to 3. Etc. Good? So the inverse function is also going to be a permutation. Now we've already proved this. How do we prove it? We proved that if a function is 1 to 1, its inverse is also a function. And so if a function is a permutation, its inverse is also going to be a permutation mapping from the same set to the same set. So if you grab a random permutation, its inverse is going to be a permutation, and pi composed with pi inverse. When you compose a function with its inverse, what do you get?
The identity?
The identity function, which is the same thing as the inverse composed with pi. Do we need to see a concrete example of that? All right, let's do a concrete example of that. So we'll scribble out some space right here. Here's my pi. Let's scribble out pi inverse, and then look at what we get when we compose the two together. So here's an example of a pi. Let's write out pi inverse. In pi inverse, what does 1 map to? 3. Maybe let's just do it without really thinking first. What's the inverse of this function? Just swap all the elements. Rather than having 1, 2, what do I have? 2, 1. Rather than having 4, 2, what do I have? Rather than having 2, 4, what do I have? 4, 2. What's next?
1, 3.
1, 3. What's next?
3, 4.
3, 4. What's next?
5.
Okay, so here's our inverse function. Right? And now I'm going to write out, doesn't matter which one we do first, which one do we want to think about doing first? Maybe we'll start with the pi. So let's do pi first, composed with pi inverse. So pi inverse composed with pi means we do the pi first, then the pi inverse, right? Let's see what this is equal to. What's it going to map 1 to? So first we start with pi. What does pi map 1 to?
2.
Pi maps 1 to 2. Now we need to plug 2 into pi inverse. So what does pi inverse map 2 to? 1. So when you run it through both, you end up at 1. Similar now, let's plug in 2. Plug 2 into pi, what do we get?
4.
4. Now plug 4 into pi inverse, what do we get?
2.
2. And so 2 ends up mapping to 2. Right?
Mm-hmm.
And then follow 3. What's 3 going to map to?
1.
1, which then maps to?
3.
And so 3 maps to 3. And notice that it wouldn't matter if we instead were doing pi after pi inverse. Start with pi inverse. Let's do that one for 4. Plug 4 into pi inverse, what do I get?
2.
Plug 4 into pi inverse, I get 2. Plug 2 into this, what do I get?
4.
4. And so once again, it's going to map 4 to 4. And then 5 to 5. Okay, there's a concrete example of what this is saying. Pi composed with pi inverse, or pi inverse composed with pi, are both just going to give you the identity function. That make sense? Now, something that you were noticing, probably, is what are these properties saying for us? Where have we seen those before? This is just for Alex, sorry. Caleb, if he was here. I don't know, did you do all of logic with us? Oh, you didn't? It's basically saying these are a group. What are your axioms of a group? You need a set together with a closed operation on the set, and if that operation is associative, there's an identity element, and there's an inverse element for every element in the set, then you have what we call a group. And so this is a concrete example of what's called a group. Okay, so there we go, properties on S of n. Mostly showing that so you can see the connection with groups, because if you continue in mathematics, you'll see other examples of groups using completely different sets, completely different operations. But continuing forward. Now, writing out permutations is really annoying. Look at how much writing I have to do for this permutation. I hate that. So we're going to try and cut down on our writing and come up with some better notation for quickly writing a permutation. So here's one valid way of writing a permutation. What does this one say? 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. So it's another way of writing this same permutation pi here. 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5.
Okay.
Just cleaning up the writing, making it easier to write and easier to read. Quickly see what something goes to. Now notice that this top line is always just going to be 1, 2, 3, 4, 5, counting up to whatever number. So all you really need is the bottom row, and you can figure out what the function was. So here's another way I can write pi. 2, 4, 1, 3, 5. What does this say? What does 4 go to? Whatever's in the 4th position. What does 1 go to? Whatever's in the 1st position. What did 2 go to? Whatever's in the 2nd position. So here's another way that we can write out a permutation.
Okay.
Good so far? Okay, so there's 2 valid ways of writing down a permutation. Now the way that we love and like the most is called cyclic notation. And so, here is how it works in cyclic notation. These are not lists, I'm writing out a function. You start with your lowest number that you haven't written yet, in our case, 1. What does 1 map to, looking at our function pi here?
2.
2. 1 maps to 2. So that's what we put next. What does 2 map to?
4.
4. So that's what we put next. What does 4 map to?
3.
3. So that's what we put next. What does 3 map to?
1.
1, which closes our cycle. And so you do n parentheses, new parentheses, and start on your next cycle. Why do we call these cycles or cyclic notation? Let's draw out a picture of our function pi there. Pi here says 1 goes to 2, so let me draw an arrow for that. And then it says 2 goes to 4, let me draw an arrow for that. And then it says,
4 goes to 3.
well, 3 goes to 1, we'll just follow in the exact order. 4 goes to 3, 5 goes to 5. Here's a pictorial way we can represent that function. that permutation. You with me so far? And notice, here's one cycle. The cycle 1, 2, 4, 3, 1, 2, 4, 3. Here's one cycle. And so that's what this is encapsulating. And then here's another cycle. 5 goes to 5. And so that's why we call it cyclic notation. It's writing out all the cycles of the function. Make sense? All right, so let's do a bigger example using all this different notation, getting used to this different notation. So here's pi.
Okay.
Question, what does 6 map to?
8.
8. It's saying 6 goes to 8, 7 goes to 1, 4 goes to 6, 1 goes to 2, etc. Just reading the notation. Good so far? Okay, let's write out its inverse. So, in the inverse function, what would 1 map to?
7.
7. Because in pi, it maps 7 to 1. In pi inverse, 1 will be mapped to 7. So it would be 7, then 1.
1.
What does it map 2 to? 1. What does the inverse map 3 to?
5.
Then what?
8.
Then what?
3.
Then what?
4.
Then what?
2.
Then what?
6.
Then what?
9.
Then what?
Close bracket.
We're done. Okay, it takes a bit of thinking. And you have to kind of look through it back and forth. Imagine that pi here had something like 50 terms. Coming up with the inverse function would have been an absolute nightmare, even with this more concise notation.
Okay.
So let's rewrite the function now with cyclic notation, and then come up with its inverse. So first off, with cyclic notation, how do we do this? And this is what's going to be on your homework. I'm going to just give you a function and say, write it in cyclic notation.
Okay.
So here's our function. Let's write in cyclic notation. What do we do first?
Start with 1 maps
Pick a number. Pick the smallest number that you haven't used yet. We haven't used any number yet, so we start with 1. Now, what does 1 map to?
to. 2.
What does 2 map to?
7.
What does 7 map to?
1.
So we end our cycle.
Okay.
Next cycle, what is the smallest number we haven't used yet?
3.
3, so we start with 3. Now, you don't have to start with the smallest number you haven't used yet. It's just a convention.
Okay.
I could have written this cycle as I could have written this cycle starting at 2, and done first 2, then 7, then 1. And it still would be perfectly valid notation. So, just convention. But following the convention, what does 3 map to?
5.
What does 5 map to?
3.
Close the cycle.
Closes the cycle. What's the smallest number we haven't used?
4.
What does 4 map to?
6.
What does 6 map to?
8.
What does 8 map to?
4.
Close the cycle. What's the smallest number we haven't used yet?
9.
And what does 9 map to? Okay, there we go. There it is written out in cyclic notation.
Okay.
Now, why do we like cyclic notation? One, it helps us picture what the function looks like. So here it is drawn out in its cycles. 2, cyclic notation, it's kind of easy to come up with the inverse function.
Because you're just reversing the cycle.
Because you just reverse the cycle. So rather than having 1 goes to 2, goes to 7, goes to 1, you instead have 1 goes to 7, 7 goes to 2, and 2 goes to 1. Where you can just go through the cycles backwards. So without even thinking, I'm just going to write these cycles backwards. 7, 2, 1. 5, 3. 8, 6, 4, 9. There's your inverse function without even thinking about it. And notice how it's going to work. 7 goes to 2, goes to 1, goes to 7. And so, since this is tracking your cycles, just going through the cycles backwards is your inverse function. So just flip each cycle around. And that's how easy it is to come up with the inverse. Think about that compared to coming up with the inverse here. And now I gave you a function with 100 elements written out in cyclic notation. How hard would it be for you to write out the inverse? Almost nothing. As hard as it is for you to write out 100 numbers. You don't even have to think about it. Okay. Now you might say, yeah, but in this one, we have the nice convention of the smallest unused number always comes next. This one now, you have a 7 first and 5. How does that make any sense? Well, since it's just a cycle, you can just right shift everything and it will give you exactly what you want. So shift everything here to the right. So I'm going to shift 7 over 1, 2 over 1. The 1 comes back around to the first spot.
So 1, 7, 2.
So now it's going to be 1, 7, 2. Shift everything 1 unit to the right, the 3 comes around. 3, 5. Shift everything to the right, so the 4 comes around. 4, 8, 6. And then 9. And so that will once again reestablish the convention if you want it written that way. This is a perfectly valid way to write it. There's no reason that this is better than this, except for that it's following that nice convention of the smallest unused number will always be next. So that's how you can quickly get it back to that way if you want it. But that's the beauty of cyclic notation. That's the way we write permutations as cyclic notation. It's wonderful notation. And a very concise way to write a function. A lot of information in it. Good so far? Okay. Now, imagine I have this set 1, 2, 3, 4, 5. What is the simplest function I can create on that set? What's the simplest permutation? The identity one, probably. The one that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, and 5 to 5. That's probably the simplest permutation you can create on it. Okay, what would be like the second simplest function we could create on this?
1 to 5.
We have 1 here go to 5.
Yeah, 1 to 5, 2 to 4, 3 to 3, 2, or 4 to 2, and 5 to 1.
That's kind of making a mess of things. I have to remember a lot of stuff.
1 to 2, 2 to 3, 3 to 4, 5 to 1.
Okay, you're not saying what I hoped you would. Which is where you just swap 2 of them.
Oh.
Rather than having 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, what if instead we had 4 to 5 and 5 to 4? So we just did one swap. So I'm calling that a swap. We just swapped those 2 places. Now it's almost the exact same thing as the identity function, except for we swapped 2 elements. Right? So I kind of think about it as like the simplest non-identity function you can create is one that just swaps 2 elements. What's the ordering that the identity function gives us? If we think about this as permutations as ordering, it's the one that gave us 1, 2, 3, 4, 5, right? If we were to write it out as identity equal to using this notation, and that 1, 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. This one now almost does the exact same thing. Let's call this the function sigma, just to give it a name. What is sigma then? It did 1, 2, 3, 5, 4. Another way of writing it as a swap. Rather than having our order 1, 2, 3, 4, 5, our order is now 1, 2, 3, 5, 4. Just swapping those 2 places. Good? Okay. A function that just does one of these swaps is what we're going to mean by a transposition. What's a transposition? It's a swap. It's just a swap. Here's its exact definition. It's a lot to swallow, but it's a simple idea. So, tau in S of n is a transposition if it has these 2 properties. Property 1, there exists I and j in the set that we're talking about, or in other words, there exist 2 elements such that they're not the same element and they map to each other. I maps to j and j maps to I. Or in other words, there's 2 elements that were swapped. Over here, in this example, our I is equal to 4 and our j is equal to 5. These are the 2 elements that we swapped, 4 and 5. So in order for it to be a transposition, there has to exist I and j in whatever set we're talking about. In our case, it's a set up to 5. Such that I and j are 2 different numbers. We can't swap 5 with 5, otherwise that doesn't swap anything. So I and j have to be 2 different numbers. And what does I map to?
J.
J. And what does j map to? What does 4 map to?
5.
And what does 5 map to? So they map to each other. So now I think you're ready to just see it and understand it. So what property does a transposition have to have? There has to exist I and j in our set, such that I and j are 2 different things, and our function maps I to j, and our function maps j to I. It's a swap.
And do we just use
Match
tau
4 to
for
5
that?
and 5 to 4. Huh?
And do we just use tau for that?
You typically use a tau for a transposition. And it has another second property. If we only swap two elements, what do all the other elements have to be?
Equal.
Map to themselves. And that's what this is going to say. So 1, there has to be 2 that swap, and 2, for all k in our set where k is not I and k is not j, then tau of k is k. All other elements have to map to themselves. 2 elements swap, everything else maps to itself, and that's what this says in very precise language. So a lot to swallow, but a very simple idea once you understand it. So let's do an example here. Tau is going to be the function that maps 1 to 1, 2 to 4, 3 to 3, 4 to 2, 5 to 5. It's a transposition because it just swapped 2 elements. Good? Now let's write it out in cyclic notation. What do I write first? 1. What does 1 go to? 1. And so there's the end of its cycle. What's next?
2.
What does 2 go to?
4.
So we have 2 goes to 4. Okay. Oops, not a comma there. What's next? 3. What does 3 go to?
3.
What's next? What does 5 go to? And notice that when we write this out in cyclic notation, all the cycles are just one element cycles, except for the 2 that got swapped. So, even more concise notation now, when it's a transposition, we will now write tau as just 2, 4, because that's the only cycle we care about. And we're saying every other cycle is a number just mapping to itself. So that is not an ordered pair, that is not an open interval of real numbers, that is a function. If you knew that this function came from S of 5, then you know this is a function that maps 1 to 1, 2 to 4, 3 to 3, 4 to 2, 5 to 5. A lot of information in a little bit of notation. Yep, that's what you have to do when you keep working with functions, is come up with more and more concise notation, so you're not filling up the board every time you want to talk about some function. Okay. Now, one of the things that we're interested in, move my camera. Not fast.
Caleb's sick apparently.
Tell him quick.
Although you probably still see
Don't get over it, just I'm here anyway. That's what I do every time.
Good. Okay. So, with these permutations, one of the ways that we think about a transposition is how's a better way I guess it can make this make sense. When you create some permutation, so say I start with the numbers 1, 2, 3, 4, 5. And I told you I want you to reorder them. Let's see what this function's doing. This function is doing 1 goes to 2, so it's doing 2, 3, 4, 5, 1. So I tell you, here's the order you start with. I want you to get the elements now in this order using swaps. How would you go from this to this using swaps? Let's move this down. 2, 3, 4, 5, 1. Move it down a little bit so we have some space. 2, 3, 4, 5, 1. Let's actually go through this exercise. So here's your order, and you're going to tell me what to swap with what, and we're going to step by step get it until it's this. So what should I swap first?
1 and 2.
1 and 2. So I can swap 1 and 2. So now we got 2, 1, 3, 4, 5. What did we do? We did a swap of 1 and 2.
I see.
Now what should I swap?
3 and 1.
3 and 1. So if I swap 3 and 1, what am I going to get? I'm going to get 2, 3, 1, 4, 5. And what did we swap there? What did we just barely swap to go from here to here? We swapped 1 and 3. You with me? Okay, now what?
1 and 4.
We could do a swap of 1 and 4, so that would be 2, 3, 4, 1, 5. And that was swapping 1 and 4. And then finally, what do we need to swap?
5 and 1.
1 and 5. So if I swap 1 and 5 now, then that would get me this. So given any permutation, I can kind of think about it as, what are all the swaps starting with the elements all in their naturally increasing order, what are all the swaps I would need to apply to get this ordering? You with me? And that is logically equivalent to saying, what transpositions can I compose together to get this function? Oh, you guys happen to pick the exact one. So pi here is this ordering. In that 1 went to 2, 2 went to 3, 3, remember this is a cyclic notation. What does 3 map to? In this function, what does 3 map to? It's cyclic notation, right? Coming back over here, what did 1 map to? 7 map to 2, map to 1.
So 3 maps to 4.
So 1 maps to 2, 2 maps to 3, 3 maps to 4, 4 maps to 5, 5 maps to 1. So notice that that is a function that has this as its input, these are as its outputs. That's what this function is. You with me? And what we just really showed is that going through these swaps right here, I can get this function from the identity function. Starting with the identity function that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, I can reorder it to get that as my final ordering going through these swaps. That is logically equivalent to saying pi is equal to the swap 1, 2, followed by the swap 1, 3, followed by the swap 1, 4, followed by the swap 1, 5.
And you don't have to add the identity at the first to compose it?
Perfect. What would happen if I did compose with identity? That is a good side note to make. What does composing with identity do?
Keep it the same.
It does nothing. Coming back to this property. So yeah, we always think about starting with the identity. Why don't we need to write that? Because it doesn't change anything. Because this already is identity, except for with the 1 and 2 swapped, which is where we started. Good so far? Now that was thinking about it. Just by rearranging elements and doing swaps, now let's actually think this through. Just think about these as functions and see how this gives us this.
Okay.
You ready? So, starting with 1, what does 1 map to? First I plug into this function. Remember that this right here is an entire function. What does this function do? It maps 1 to 2, 2 to 1, 3 to 3, 4 to 4, 5 to 5. That's what this function does. It's a transposition.
Okay.
So, plug in 1, we start with this. What does this map 1 to?
2.
2. And now we take the 2 and plug it in here. What does this map 2 to?
2.
And what does this map 2 to?
2.
And what does this map 2 to?
2.
And so when it's all said and done, when you run 1 through the composition of all those functions, you ended up with
2.
2. Now let's run 2 through them all. What does this map 2 to?
1.
1. What does this map 1 to?
3.
What does this map 3 to?
3.
What does this map 3 to?
3.
And so when it's all said and done, 2 went to
3.
3. Once again, what does this map 3 to?
3. 1. 4. 4.
And so 3 goes to 4. Plug 4 in.
4. 4. 1. 5.
Finally, plug 5 in.
5. 5. 1.
And so now notice, let's write this out in cyclic notation. What does 1 go to?
2.
2. What does 2 go to?
3.
What does 3 go to?
4.
What does 4 go to?
5.
What does 5 go to?
6.
Which ends our cycle. So we get back to where we started. So notice that, just thinking it through, those series of compositions, okay,
Olivia Caleb Brooklyn.
what you said.
Olivia Caleb Brooklyn.
Okay, Birmingham wants to have closing at 11:50.
Okay, thanks. So notice, we thought about it one way, just think about what are the swaps I have to do to get from here to here. And then we actually thought about it, think about those as functions and plugging the input, and we see that they are giving the exact same thing. And so that's what a transposition is. We can think about it as high level as a swap. And we think about this as decomposing a function into a bunch of transpositions. This is kind of like the counterpart to doing factoring a number into its prime numbers. Splitting a number up into its prime numbers, it's kind of like take a function and split it up into its transpositions. What are all the swaps you need to ultimately compose a function, the permutation that you're talking about? Good? Now, hopefully you saw the pattern here for how you came up with these transpositions. You do those two, followed by those two, followed by those two, followed by those two. And that's just the pattern for actually computing one of these by hand. And that's the pattern that the author teaches you in the book. That is not the way that I decompose them myself. Here's the way that I do it. It's just a pattern that you memorize so that you don't have to think it through every time. And you can just instantly know how to decompose it. Here's the way that I do it. I do those two, followed by those two, followed by those two, followed by those two. And it also works. So whichever pattern you want to memorize so that you can quickly decompose some function, you can use whichever one you want. Here's the author's way of doing it. So take a function in cyclic notation, represent it as a bunch of transpositions. Here's one way to do it. Here's the way that I like to do it. Now, notice that these are not the same thing. How many different transpositions, how many different ways can we represent the same function using these transpositions? As many as we want. Because notice, what if I start out the transposition with swap 1 and 3 and swap 1 and 3? So this says swap 1 and 3, put them back. Now I'm back where I started. And now do all this. It doesn't change anything. And so I could have made this infinitely long. Does as many swaps as I wanted. So there isn't the right way to break it up. There are just ways to break it up. Let's quickly see that this gives us the same thing. So let's go through these steps and see if it gets us to the same point. So following my steps, what do we do first?
You switch 1 and 2. Oh.
Right to left. Switch 4 and 5. So now we get 1, 2, 3, 5, 4. Now switch 3 and 4. 1, 2, 4, 5, 3. Now switch 2 and 3. 1, 3, 4, 5, 2. Now switch 1 and 2. 2, 3, 4, 5, 1. And it worked. And there's no reason that you have to follow some pattern. You could have just thought this through. So let's do one more ourselves. Because last time you guys happened to pick that one. Let's just come with ourselves. Let's see. Let's start by getting 4 in its position. So I'm going to swap the 3 and the 4 first.
Okay.
So I'm going to do 1, 2, 4, 3, 5. What did we swap?
3 and 4.
3 and 4. Okay, now what should I get in this position? Well, now I'll get the 1 where it goes. So I'll swap the 1 and the 5. So then I'll do 5, 2, 4, 3, 1. You with me?
Mm-hmm. Can you swap 1 and 5?
Ah, yes. I swapped the 1 and the 5. Okay, what should we swap next?
Let's get the 2 in the position.
Alright, so should we swap the 2 and the 3?
Yeah.
So you're saying 5, 3, 4, 2, 1. And that was, what did we swap? I forgot. 2 and 3?
3.
Okay, and what's next?
Switch the 5 and the 2.
5 and the 2. We swap now the 5 and the 2. Then that would get us 2, 3, 4, 5, 1. And if you were to go check, it would be the case that pi is equal to, remember, write your last one first. 5, 2, composed with 2, 3, composed with 1, 5, composed with 3, 4. And if you'd actually write it through, go through all those, you'd see that that's the result. Let's pick one random number and follow it through to see if it worked. Let's see what 3 maps to. When I plug 3 into this, what do I get? 4. When I plug 4 into this, what do I get? When I plug 4 into this, what do I get?
4.
4. When I plug 4 into this, what do I get?
4.
4. When I plug 4 into this, what do I get?
4.
4. And so you see, this is just tracking where each number went after each swap. You're just writing out the history of how all the different numbers would map through this thing. If I plugged 1 into this thing, it would go from 1 to 1 to 5 to 5 to 2 to 2. That's all it would do. Make sense? Okay, so once again, let's try this with a more convoluted example. Here's pi, written in cyclic notation. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes back to 1,
Okay.
etc. Understand the function?
Mm-hmm.
All right, let's now write this out as a composition of transpositions. You are not expected to write out the numbers, although you could. You could write out all the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can see the final order that this is saying. So this is saying our bottom would be 1 goes to 2, 2 goes to 3, etc. And fill out your bottom. And you could just manually think through all your swaps and do it. And that would work. Nothing wrong with that. Or you could memorize some procedure to quickly give you the answer. So let's do it memorizing the procedure. Should we do it the author's way or my way?
Your way.
My way. So using my way, what do we do? The example I showed you in my way was written out right here, which is compose those, then those, then those, then those, next cycle. So for my way, you would write 1, 2, composed with 2, 3,
2, 3.
composed with always one overlap.
3, 4.
3, 4,
4,
composed with
4, 5.
4, 5. And that ends that loop. Next, composed with
6, 7.
6, 7, composed with
7, 8.
the 9. We're never going to swap it. It's already in its starting position is another way that you can read that.
Don't do anything.
So don't do anything with 9. We go straight to 10 and 11. And there we go. There it is as a bunch of compositions. You could write this out, following where it goes if you want. Let's just do one number to plug in to see if this actually works. Which number should we plug in?
3.
3. Knowing our function, 3 better go to 4. Right? So let's see if that is in fact the case. Remember, you start here. This maps 3 to
3.
this maps 3 to
3.
3 to 3 to 3 to 4 to 4 to.
4.
Anyways, all of a sudden that 3 went to 4. Okay. Surprise, surprise. So there's a group procedure you can just memorize for how to do these quickly, or you can do it the author's way. That works too. Or you can calculate by hand. Whatever you want. Good? Okay. Now we already talked about when I represent a function, when I represent a permutation as a bunch of transpositions, we can use an infinite number, because I can keep swapping the same element back and forth as many times as I want. Or I could possibly go on some big cycle of swap the 1 with the 3 with the 2, the 1 with the 3 with the 2, the 2 with the 1, the 1 with the 3 with the 2, the 2 with the 1. I can set these infinite cycles. And so, how many transpositions can I use to represent a particular function?
Infinite.
Potentially infinite. But it turns out, if I can use an even number, then I can always and forever only use an even number of transpositions.
Because to switch them, you have to switch.
Because once you switch, you have to switch it back. It's some intuition you can have in your head. But you might think, I don't know, aren't there clever cycles of like using 3 I could use that get me back where I started? And this is going to say no. There's no clever cycle of 3, there's no clever cycle of 5, there's no clever cycle of 7. You have to use an even number to get back where you started. And that's essentially what we're going to prove. So first off, we call a permutation even or odd, one of the two, provided it can be expressed as an even or odd number of transpositions composed together. So let's see, this one up here, how many did it use? How many transpositions to get pi here?
5.
It happened to use 4.
Oh, yeah.
So always and forever, no matter how many ways you come up with representing this as transpositions, it's always going to be an even number of swaps. You could have used 4, you could have used 6, you could have used 8. But it would have been impossible to create pi here using 7 swaps. Couldn't have done it. We're going to prove that. But so pi here is going to be an even function because it was represented as an even number of transpositions. What about this pi? How many transpositions was it represented as?
1, 2, 3, 4, 5, 6, 7.
7. So pi here is going to be an odd one. Now, is there a way that just quickly looking at this, I could instantly say whether it was even or odd without actually coming up with a bunch of transpositions to represent it? And the answer is yes. I'm going to show you how to do that. So you can instantly know if it's even or odd without having to come up with some series of transpositions. That will be where we ultimately end.
Okay.
Ultimately, what are you going to check? I'll give you the formula right now. You take n, where n is however many elements we're using. In this case, n was 11. In this case, n was 5. And you subtract however many cycles your function has. How many cycles does this function have?
1.
1. So up here, so n minus, I'll just write out cycles for now. We'll have a way of representing that. N minus cycles. Up here we had 5 minus 1 is 4. So it was going to be even. This one, how many cycles does this function have? 1, 2, 3, 4. 4 cycles.
And will that always end up as
And so if you do 11 minus 4, you get
7?
7. Yeah.
Will that always end up how many you're gonna have? Or
Will you
just
always be able to
even
come up with 7 transpositions to represent your function? If that's the number here, is what you're asking. And the answer is going to be yes. So you'll always be able to get that many. And on top of that, once you get a particular number,
You know that
you won't be able to get another even or odd number. If you get an odd, always and forever will be odd. If you get an even, always and forever, it will be even. Good? Now we're going to prove all that. I'm just priming for where this is going. Okay, so that's what it means to call a permutation even or odd. The sign of a permutation. The sign of a permutation, we're going to call it +1 if it's even, and -1 if it's odd. So sign of some permutation pi is going to be +1 if pi happens to be even, and -1 if pi happens to be odd. Just definition, to assign some number to it. Good? Okay, so with that, let's note one more thing. So if I tell you pi is represented as a composition of n transpositions, then what is the sign of pi? Remember, the sign of pi is +1 if n is even, and it's -1 if n is odd. So another way we could represent that is the sign of pi is just -1 to the n. What's -1 to an odd number? -1. And what's -1 to an even number? Just 1. So that's why this works. So what is the sign of pi, if pi can be represented as n transpositions? It's just -1 to the n. And that's just a quick way of, if your function's even, giving it the number +1. If your function's odd, giving it the number -1. Okay. So now let's prove our first theorem here. Our first theorem, we're going to prove that if pi and sigma are 2 permutations, then the sign of pi composed with sigma is going to be equal to the sign of pi times the sign of sigma. So this is times as in multiplying numbers. This is composition as in functions.
Okay.
This takes 2 functions, gives us a function, and then the sign spits out a number. This takes the sign of a function, which is either going to be 1 or -1. This takes the sign of a function, which is going to be 1 or -1, and then multiplies them together. Good so far? We're going to prove that those are equal. Okay, so let pi and sigma be 2 permutations. And let's assume that when we get our transpositions for pi, and then it's represented as x transpositions. And let's assume that when we get our transpositions for sigma, it can be represented as y transpositions. So what is pi? It's some number of x transpositions all composed together. And sigma is y number of transpositions composed together. Good so far? Okay. So then, what is the sign of sigma composed with pi? How many transpositions did we use for sigma?
X or Y?
Y. How many transpositions did we use for pi?
X.
X. So the sign of sigma composed with pi is just going to be -1 to our total number of transpositions. If x plus y happens to be even, then it's going to come out +1. If x plus y happens to be odd, it's going to come out -1. Good so far? Now back from your algebra, -1 to the sum of 2 exponents is the same thing as -1 to the first exponent times -1 to the second exponent. When you have something like 2 to the 2 plus 3, this is the same thing as 2 squared times 2 cubed.
Yeah.
That's the only rule we're using here. Follow that? And then by definition, what is the sign of sigma?
-1.
It's the -1 to the number of transpositions you use to get sigma. And what is it? -1 to the x, or sorry, what's the sign of pi? It's -1 to the number of transpositions you have to use to get pi. And so the sign of the composition is equal to the product of the signs.
Okay.
Make sense? Okay. So now, ready to move on to the fun stuff.
Are these just example problems that we're gonna have to solve on homework?
No. What these proofs are will be much harder than anything you have to do on your homework. Not that they're hard proofs, but that they're hard in all the notation. Like it's hard for you to see sine of two Greek letters composed together and remember in your head, oh, that's a function composed with a function, gives me a function, sine of the function. Okay, now this is either the number 1 or negative 1. And I know that's a lot to try and consume. And keeping that in your mind as we go through these proofs is difficult. But when it's all said and done, remember, big picture, what am I after with in this whole section on permutations? Getting you comfortable with functions and function composition. And so we've been doing a ton of functions and a ton of function composition. Thinking where one function maps, then the next, and the next, and the next. That's the whole motive for this. And then this is just a cool proof. All right, so let's go through the cool proof. So, notice something. So if pi and tau are in S of n, where tau is a transposition, then pi composed with tau either has one more or one less cycle than pi did. So now think about a function, think about these permutations in terms of cycles. We can think about transpositions rather than think about them as swaps. That's one way we can think about them. We can also think about them as they either glue cycles together or break cycles in half into 2 cycles. And that's why I'm going to try and give you intuition for right here. So let's say that pi is this function. I'm representing it pictorially. So it's a function, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 6 goes to 7, 7 goes to 8, 8 goes to 9, 9 goes to 6. Here's pi written out in cyclic notation, but I also want you to see the picture. Here's a picture of the cycles. Notice 2 cycles, 2 cycles. With me so far? Now I'm picking some random transposition. I'm going to pick transposition 4, 7. Okay. So we're going to swap 4 and 7. What happens when I swap 4 and 7, it makes like whatever 4 used to go to, 7 now goes to. And whatever 7 used to go to, 4 now goes to. Okay. So, what does 4 go to in this picture?
5.
5. So instead of 4 going to 5, this transposition is going to make 7 go to 5. And what does 7 go to in this picture?
8.
8. So now instead of 7 going to 8, we're going to have 4 goes to 8. That's what composing with 4-7 did. Or sorry, that's what composition with the transposition 4-7 did. And notice what it did is it took those 2 loops and glued them together. And the result is this now. So down here I'm calling sigma. What's sigma? It's whatever you get when you get pi composed with that transposition. With me? And now, let's compose that with 4, 7. What does that do? Well, now, whatever 4 goes to, 7 is going to go to now. And whatever 7 went to, 4 is going to go to now. And so it takes that big loop and it breaks it up into 2 loops. That's pictorially what it does. So each transposition, if you pick 2 elements from different loops, it's going to glue those loops together. If you pick 2 elements from the same loop, it's going to break that loop apart. With me? And then let's just think it through to make sure that this is in fact the correct picture. So we're saying with our picture, 7 should now go to 5. Let's see if that's the case. Let's plug 7 into this. So plug 7 into this transposition, what do we get? 4. Plug 4 into pi, what do we get? 5. So now 7 goes to 5. Okay. Similarly, down here, we're saying sigma composed with 4, 7 should now make 4 go to 5. So let's check that. Plug 5 into this, what do we get? Or sorry, plug 4 into this, what do we get?
7.
7. Plug 7 into sigma, what do we get?
5.
And now 4 goes to 5. So go back, draw this now how sigma is. So here's sigma. And draw this back to how pi was. So when you compose with a transposition, if the elements come from 2 separate loops, it glues the loop together. When you compose with the transposition, the 2 elements come from the same loop, it breaks the loop into 2 different loops. So each transposition either breaks a cycle or adds a cycle. Make sense? Okay. So, getting to find a new function, just to talk about the number of cycles here. So definition, let pi be some permutation, then C of pi is going to be some function that just spits out the number of cycles in pi. So if I plug this function pi into C, what does it give me? 2, because there's 2 cycles. If I plug sigma into C, what does it give me? 1, because there's 1 cycle. If I were to plug this function pi into C, what would it give me? 4, because there's 4 cycles. With me? Maybe one more trick question. Let's say I took I in S sub 20. Or sorry, not iota. In S sub 20. So it's the identity element. How many cycles in I?
1. Wait, no. 20.
20. Because it does 1 to 1. That's a cycle. 2 to 2. That's a cycle.
3, 3, 4, 5.
Okay, you with me? So if iota were in S sub 20, then C of iota in this special case would be 20. So I think you're following me now. Just notation so that we can have a way of writing the cycles. Rather than over here, notice what I did. Oh, now you erase it. When I told you the formula, I said n minus the number, the cycles. Here's going to be how we say the cycles. So C of pi from above is 2. C of sigma from above is just 1. Good so far? Now, remember, when we compose with a transposition, we did one of 2 things. We either broke a cycle into 2 cycles, or we glued 2 cycles together into 1 cycle. Had to be one of those 2 cases. Right? And so, notice, then, pick any permutation pi. When you compose it with the transposition, then the number of cycles you have will be what you had before the transposition, plus or minus 1. Plus 1 if you broke a cycle into 2 cycles, minus 1 if you glued 2 cycles together. That make sense? Mm-hmm. Each transposition can only change the number of cycles by 1. And it has to change the number of cycles by 1. It either had to glue 2 together or break 2 apart. There's no other thing you could have done. Okay. So, we've already answered that question. How many ways to write pi, if pi is equal to that in S of 5? How many ways to write it as a composition of transpositions? Infinitely many ways. But it's always going to be an even number if it's an even number, an odd number if it's an odd number. I intend to have that conversation here, but we had it earlier. Okay, so with that, here's what we're going to prove. If pi is in S of n, if pi in S of n, this permutation, can be represented as a number of transpositions and b number of other transpositions, where each t sub k and sigma sub k is a transposition, then a and b have the same parity. Or in other words, they're both even or they're both odd. We can't represent as an even number of transpositions one way and an odd number of transpositions another way. We're proving that's impossible. If you represent it as an even number of transpositions, always and forever it will be an even number of transpositions. And same with odd. That's all we're saying here. Okay? Here's what we're going to prove. Almost. We're going to prove something a bit more rigorous than this. This is just give you intuition for what we're proving. Here's actually what we're going to prove. We're going to prove that if pi is in S of n, where pi can be represented as A transpositions, then A will always be congruent mod 2 to n minus the number of cycles in pi. Now this is exactly what I told you before. I said we look at n minus the number of cycles in pi. If this comes out even, then whatever the number of transpositions you use to represent pi will always be even. What does it mean for 2 numbers to be congruent mod 2? It means that they're both even or they're both odd. Do you remember congruent mod 2, or do we need an example? Let's see exactly what this meant. Is 17 congruent to 5 mod 2? How do we check that?
It is...
What's 17 minus 5?
12.
12. Does 2 divide 12? Yes. So those are congruent mod 2. Is 18 congruent to 5 mod 2? Well, that would mean that 2 divides 18 minus 5 is 13. Does 2 divide 13? No. Now, if I put a 10 here, 18 minus 10 is 8. Does 2 divide 8? Yes. So it's going to be true if both numbers are even or both numbers are odd. So this is going to be our way of saying both numbers are even or odd. Rather than saying it in a bunch of words, here's a concise way of saying 2 numbers are either both even or they're both odd. You say they're congruent mod 2. So A is going to be our number of transpositions, and then this number is just a constant for whatever function you give me. If you give me this function right here, pi, what's n? 11. And how many cycles are there? 4, which comes out to, in that special case, it's 7. So I'm saying any number of transpositions you use to represent pi is going to be congruent to 7 mod 2. So once you pick a function, this is a constant. A is the number of transpositions you choose to represent that function. And we could represent with 7 transpositions, but I could have also represented with 9, or 13, or 101. Make sense? That would work as well. So, this is going to be a constant, some number. So what are we saying? If pi is a permutation, where pi can be represented as A transpositions, then A is always congruent to this number, mod 2. Where this number you can just calculate right out the door just looking at the function. So you can instantly know just looking at a function whether or not it's even or odd.
Okay.
Make sense? And that's what we're now going to prove. Okay, so here comes the proof. The cool part of all this. So let pi be some permutation such that pi is equal to one transposition composed with the second, composed with the third, composed with tau sub A. So it's going to be A transpositions composed together gives you pi. My job is to prove that A is congruent to n minus the number of cycles mod 2. You with me? Okay. Now I'm going to say consider, starting with the function iota. And then just the first transposition. And then the first transposition composed with the second. And the first composed with the second composed with the third. And then the first composed with the second composed with the third composed with the fourth. Until you compose together all A transpositions. Let me write that out in a table for you. So here's starting with just iota, just the identity function. Now, when you plug in the identity function, what is n minus the number of cycles in it? Let's write out a concrete case. What you said over here. If iota came from S sub 20, how many cycles are in iota? 20, because it maps 1 to 1, 2 to 2, 3 to 3, 20 to 20. Okay, so now what is n minus c of iota equal to then? What is n? It's the number of elements we're using. How many elements did we use? 20. Minus the number of cycles? 20. And you get a big fat? 0. So when the permutation we're talking about is iota, then n minus the number of cycles in it is always and forever going to be 0 for any identity function. Right? Mm-hmm. And now we do our first swap. How many cycles now after we do, well, yeah, we can think about it that way. Now I do one swap. How many cycles does my function have?
19.
N minus 1. Before it had n cycles. Because we map 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6. If I map 1 to 2 now and 2 to 1, that makes 1 2-element cycle. So I decrease my number of cycles by 1. Concrete case. Let's start out in the number 5. 1, 2, 3, 4, 5. Think about pictorially with the identity function. It maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. Right? Now if I do one swap, give me some transposition. Give me transposition, any transposition for 1 through 5. 3 and 5. 3 and 5. So now what does this do? It makes that 5 maps to whatever 3 used to map to. I may have redrawn my 5 down here for the sake of the picture. So now it's going to map 5 to whatever 3 mapped to, and 3 to whatever 5 mapped to. And so now how many cycles do we have? 4. So before we had 5 cycles, now we have 1 less after performing a transposition. So, n minus the number of cycles, since our number of cycles decreased by 1, then this total sum goes up by 1. Rather than doing like 20 minus 20, it's now 20 minus 19. And so, after one transposition, this number has to be 1. With me so far? Okay, now we do another transposition. One of two things. We either broke the cycle and made so that 3 goes back to 3 and 5 goes back to 5. That's one thing we could have done. Or we could have added something else on to the cycle we created. And we could have made it so that now 5 goes to 4, goes to 3, goes to 5. Something like that. So either we broke the cycle we just made, or we added to our cycle. In either case, we either increase our number of cycles by 1 or decrease our number of cycles by 1. We couldn't have left the number of cycles alone. And so, when you compose with another transposition, you had to either subtract or add 1 cycle, which meant this total sum had to increase or decrease by 1. Okay, and then once you got that step, I think these steps are all trivial. So now, compose with another transposition, you have to subtract or add 1. Compose another transposition, you had to add or subtract 1. Dot, 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 you have to add or subtract 1 by the time we get all A of our transpositions, which gives us our initial function. Now here's the important point to note. How many of these 1s that we plus or minus together do we have? We had 1 for our first transposition, 1 for our second transposition, 1 for our third transposition. If it's a total of A transpositions, how many 1s do we have here that we're plus or minusing together? A of them. And now if A is an even number, then plus or minusing 1 an even number of times is going to be an even number. And if A is an odd number, then plus or minusing 1 an odd number of times is going to be an odd number. So then, this column, n minus c of pi, this final row of this column, is going to be even if A is even, and odd if A is odd. Therefore, A is congruent to n minus the number of cycles mod 2. There it is. Proved it. So now you can just look at this picture, and that's why we can quickly just look at this picture. This picture right here. I can say 11 minus 4 cycles, 7. Yeah, that's an odd. And there's a proof that you can just look at like that and instantly know. Some quick corollary that follows for free. Pick pi and s of n, then the sign of it is just -1 to whatever this number is. So if that number comes out even, then the sign's going to be +1. If the number comes out odd, the sign's going to be -1. So you can quickly, instantly get the sign as well. Okay, so pretty interesting, the things that you can prove working with functions. I know this is completely new and completely strange working with functions this way. Again, what's my big motivation for all this? Just to try and get you comfortable with this symbol right there. That's what I really want, is for you to just be comfortable with compositions. It's something that you use in math over and over and over again, and students don't think very much about when they see it, and it's just everywhere. So that's the real thing I'm trying to stress with all this. But interesting field of mathematics going into permutations, counting the number of ways you can organize things. It might not appeal to your intuition right out the door, but say you wanted to count the number of possible combinations for a Rubik's Cube. This is relevant mathematics. Anyways, that's it for today's material. Any questions that you want recorded? All right. Well, good luck to you then. Test next week. Don't forget.